Welcome to our channel Biswanka's Math Exclusive. This is my part 4 video on topology. For better understanding, see my previous videos. Now start with this. Everywhere dense or simply dense. A subset G is X tau is said to be everywhere dense if capital X. A subset G is X tau is said to be everywhere dense in X if G bar equals to capital X. Here is an example. A equals to closed interval AB. Then A bar equals to closed interval AB equals to A. That is A bar equals to A. Nowhere dense when G bar not equals to X, that is interior G bar equals to phi, then it's called nowhere dense. Here is an example. A equals to 0 1, open interval 0 1, all rationals implies since every subintervals contains rational as well as irrational. Then interior of A bar equals to phi. Dense in itself. A subset of R is said to be dense in itself if every point of A is the limit of A, that is, it has no isolated point, that is A bar equals to A. Now separable. The topological space X tau is said to be separable if there is a countable dense subset in X, that is A1, A2, A6 are all dense subsets. Example, the set Q of all rationals in R is dense in R with respect to usual topology of R because of the fact that between any two reals there are many rationals. Next example, there is a non-empty proper subset of reals with usual topology which is both open and closed. Is it true or false? Give reason. Let A equals to 2 by 1, 3 by 2, 4 by 3 subset R, then A equals to 1 plus 1, 1 plus half, 1 plus 1 by 3 equals to 1 plus 1 by n, where n belongs to capital N. Here limit n tends to infinity, 1 plus 1 by n equals to 1, so dA equals to 1. Since 1 not belongs to A, so A is not closed and open, as 2, 3 by 2 are all isolated points. Next, consider the topology tau on the set N of naturals with consist of phi and all the subsets of N of the form An equals to n, n plus 1 where n belongs to capital N. Then find A to the power D, where A equals to 3, 19, 29, 41. Given tau equals to phi n A1, A2, A3 now n1 equals to nbd of 1 equals to A1 n. Here A1 n contains 3, 19, 29, 41 other than 1. So 1 is the limit point. Next n2 equals to A1, A2, n. Here A1, A2, N contains 3, 19, 29, 41 other than 2. So 2 is the limit points. Similarly, we get N40 equals to N A1, A2 dot A40. Here all subsets contains 41 other than 40. So 40 is the limit point. Similarly, N41 equals to N A1 dot A41. Here A41 not contains 3, 19, 29 other than 41. So 41 is not the limit point. Thus AD equals to 1, 2 dot 40. Next theory. Let X tau be a topological space and A be subset X, then show that A bar minus B bar equals to A bar B A minus B whole bar. Proof. We have A intersection B subset A implies A minus A intersection B subset A implies A minus B subset A implies A minus B whole bar subset A bar. Numbering it equation 1. Similarly, B bar A bar subset B bar, numbering it equation 2. Now from 1 and 2 we have A minus B whole bar minus B minus A whole bar subset A bar minus B bar equals to A bar minus B bar implies A bar A minus B bar subset A bar minus B bar, numbering it equation 3. Again A minus B equals to element of A which does not belongs to B. Although some limit point of A is common to the limit point of B, then A bar minus B bar subset A minus B whole bar. From 3 and 4 we get A minus B whole bar equals to A bar minus B bar. Proved. Next theory. So that the intersection of two dense subsets in a topological space X is dense in X. Start the proof. Let A and B be two non-empty subsets of X given that A bar equals to X, B bar equals to X. So A bar intersection B bar equals to X. Again we have A intersection B bar equals to A bar intersection B bar equals to X. That is A intersection B bar equals to X. Thus the intersection of two dense subsets of X is also a dense subset of X. Next, Kuratowski's closure operator. Define a Kuratowski closure operator on a non-empty set X. If C is Kuratowski closure operator on X, then show that tau equals to G belongs to, that is G subset X, where C X minus G equals to X minus G, forms a topology on X such that CA is the tau closure of A for any subset A of X. Now a definition: an operator that assigns to each subsets of A of X another subset of X denoted by AC is called a Kuratowski closure operator if the following four axioms known as Kuratowski closure axioms hold. Here I put a small note that when A bar equals to A union A dash equals to AC subset X, it tends to 0 as n tends to infinity, but 0 not belongs to A. AC subset X is not possible. K1 such that phi C equals to phi K2 for any subset A of X, A subset AC. 3 for any two subsets A and B of X, A union B whole C equals to AC union BC. K4 for any subset A, AC whole C equals to AC. Now for second part, here phi and X belongs to tau because their complements X and phi are respectively members of tau. Here I put a note. Then x minus g c subset x minus g alpha c equals to x minus g alpha because x minus g alpha is a member of tau. This is true for every alpha belongs to index or delta, and therefore x minus g whole c equals to intersection alpha belongs to delta x minus g alpha equals to x minus union of alpha belongs to delta g alpha equals to x minus g. That means x minus cc, x minus gc equals to x minus g, and it is a member of tau, and hence g belongs to tau. Again we have the intersection of any two members of tau is a member of tau, so tau is a topology on X. It remains to show that for every subset A of X we have AC equals to A bar equals to tau closure of A. Now A bar equals to intersection of all tau closed set each containing A equals to intersection of members of tau each containing A, and therefore A bar is a member of tau with a subset A bar. Using Kuratowski's closure axioms we get AC subset A bar C equals to A bar. Again by Kuratowski axioms we get AC whole C equals to AC, where A bar subset of AC implies A bar subset AC. From 1 and 2 we get A bar equals to AC. This is the theorem. Definition of closure. Let X tau be a topological space and A subset X the intersection of all tau closed superset of A is called the closure of A and is denoted by A bar or CA or CA or CLA, C minus A. So there is my topic end. Hope this video is helpful for you. If you find this video is helpful for you, please like and share with your friends and subscribe for this type of video. Thank you.